Welcome to the winter edition of the Recharge Zone podcast. This is your host, Brent Doty. I'm joined here with Ann-Margaret Gonzalez and our special guest today, Jim Winterle from the modeling group. Jim is a director under Aquifer Management Services, and he heads up a team of individuals who collectively help model the aquifer. So today we'll be learning all about what a model is and what it's used for and what the future holds in our modeling program. So to start out, Jim, can you tell us a little bit about yourself and your role here at the Edwards Aquifer Authority and what led you to get into modeling and aquifer modeling?
Sure, Brent. I've always kind of been interested in geology, but didn't want to work at a mine or oil production. So I found the field of hydrology and got my degree at master's and bachelor's in hydrology at University of Arizona. Then I spent my first job out of there was in Texas at Southwest Research Institute, where I spent about 15 years modeling for safe nuclear waste disposal. And we got into all sorts of complex models in that kind of field. But I started really wanting to work on a local job that benefited the community and found the Edwards Aquifer to be the kind of place I was interested in. And they had an opening 9 years ago at just the right time. So I fell into that spot perfectly, and I feel like we came into the program that kind of needed a little life put into it, and we were able to take it with our team and accomplish a lot and get it going in a really good direction, I think.
So what is modeling? I mean, I know it's more complex than this, but it's essentially like computer modeling, putting data in to get like a depiction of something, right?
Right. Yeah. So, a model is just a representation of something. A fashion model represents the clothes they're wearing. A model airplane is a representation of an airplane. Well, these are computer simulations, or it could be simple as a basic equation that represents some physical process, where that if you know your inputs, you can predict an output. So in our case, we know, or we can estimate, how much recharge and pumping goes on in the aquifer. And based on those inputs, we would like to be able to simulate an output, which is the spring flows at Comal and San Marcos Springs, and perhaps water levels at the index wells. So you construct these computer models to be able to simulate that. So basically, if I could try to describe how it works, it's just a numerical grid. If you just look at a network of square cells about a quarter mile by a quarter mile each that cover the whole Central Texas region from just south of Austin all the way out into Kinney County past Uvalde. There's about 400,000 different computational cells in the model.
Wow.
Each one of those gets represented by some property. You tell them, the computer, well, how thick is each layer? How much water can it store for a given amount of pressure that it's under, and how easy or how hard is it for water to flow through there. We call that hydraulic conductivity. So you specify those, and you, a little bit by trial and error and a little bit by expert judgment and data, you adjust those properties. And then you've also got data that's been collected for the last going on 80 years now for pumping and recharge to the aquifer. We can put those in as inputs. And we go through a process called calibration, where you adjust those fixed properties, storage and conductivity and a few other things. And you manipulate those until your recharge and pumping inputs result in a computer simulation that matches what was observed in terms of the spring flows and water levels. So basically, you're taking a historical data set and you're making your model match that.
So we're on the cusp of celebrating our 25th anniversary at the EAA. So the EAA's models, like, how are they developed? Do we have like field techs that go out and collect these data sets? And what kind of data sets do you all collect to calibrate the models?
Yeah, for the model, you need observations that you're trying to match. And those are water levels at over 1,000 wells throughout the region. We have observations of water levels, and that's thanks to the data collection program going back way before the EAA, the U.S. Geological Survey, Texas Water Development Board, but EAA itself, since its foundation, has a great data collection program that make it possible. Because you don't have good data, you can't have a good model.
Basically, if you have garbage coming in, you're going to get garbage coming out.
Yeah.
So with these models, it all comes down to the quality of the data that you put in there. Is that right, Jim?
That's right. And then there's also the skill of the model that kind of you're almost sculpting a set of properties based on a lot of judgment and data and observations to try to get it to predict. And that process can take years. In fact, the groundwater model we used to support the habitat conservation program, that's original version of that got started around 2002 and came to the first final version of it in 2004. We've since totally updated it and kind of reimagined some of the properties and how things are set up there. But largely it's just very similar to the original model, but we find it's a little bit better at predicting. And since 2004, we obviously have another decade or more of data that we can run the model forward and see how well it's matching. And as I was mentioning to you earlier, Brent, this model actually does a pretty good job. It generally, we're predicting average monthly flow rates, so we're not like trying to say what the flow is any given second, but as far as predicting the average monthly flow rates at the springs and the water levels during the month, it does a really good job, I think. And it's been reviewed. We had the National Academy of Sciences had an expert panel review it, and they found that the model was suitable for what we're using it for. And I can talk a little bit more about what we use it for. We've also had our own local experts involved in helping to review and give feedback. So we don't want to make sure, because we're a small shop, the modeling team is just 4 people, and we want to make sure that if we start off on a wrong path, we'd like to identify that early. And having a lot of different outside collaborations and expert reviews, I think really keeps us in the right direction, and also it makes our model a lot more transparent and defensible, because it's been presented to not just all these experts, but also throughout the process, the stakeholders in the habitat conservation program have also been.
I'm glad you mentioned the Habitat Conservation Program, HCP. Back in October, we had a podcast with Christy Kolas. She's a biologist with the HCP program, talking about some of the different creatures and endangered species that live in the springs. And from what she was saying, that they really depend on a minimum base flow. So we know back in the Drought of Record, which is, if you look throughout the history of our records about the aquifer, the worst drought occurred in the 1950s. And that's when Comal Springs went dry for 6 months. And that's the same kind of thing that we're trying to prevent right now, based on what Christy and others have told us, that these species need this minimum spring flow, about 30 cubic feet per second, to survive. So does the model play into that along with the HCP, or how does the model affect those programs for the Habitat Conservation Plan?
Yeah, that leads right into my question, is like, once we got a calibrated model, what do we use it for? Because having a model that matches what you already know happened in the past doesn't really do you any good. But once you determine that your model can match observations, then you can do what-if scenarios or any kind of scenario. And you mentioned the Drought of Record. So for the Habitat Conservation Program, I guess it was agreed by all the stakeholders that the goal should be that you could maintain the minimum flows that you mentioned if we were to repeat that Drought of Record where in the past the aquifer went dry. So they have to come up with conservation measures that reduce the amount of pumping that goes on in the aquifer in order to sustain that spring flow. Well, how do you know how much you have to reduce it? And there's no way to live these scenarios, so that's where the model comes in. So you tell the model you've got a set of recharge conditions that happened in the 1950s, but instead of pumping like you did in the 50s, you say, what if everybody who has a permit to pump can pump their full allocated amount? And that's like 472,000 acre feet of water per year. And then plus exempt pumping is another 14 or 15,000 acre feet for domestic wells and livestock. So if you're pumping that much water, which is way more than was pumped in the 50s, and your spring went dry in the 50s, it's going to go dry. So now you can start thinking about what are your conservation measures? Well, the one most people are familiar with is this stage 1 through 5. As the water levels go below certain things, you got to stop watering your lawn every day, and the restrictions get increasingly more severe. So by the time, if we've never been in stage 5, but if we ever did, that's a full 44% cutback permit holders would have to reduce their pumping by.
So the model was used to it was the catalyst for the critical period management that we rely on now for our jurisdiction and our region.
Right. So that's the Habitat Conservation Program had 2 phases. One was just to get the initial permit to protect the endangered species, called an incidental take permit. That may be a little technical for what some people care, but basically it prevents the federal government from intervening on our use of the aquifer water, as long as we have an agreement with them that we're going to manage it in a certain way that preserves those spring flows because of the endangered species. So in addition to those conservation measures, the stage 1 through 5 restrictions, we also have something called Voluntary Irrigation Suspension Program, where it's purely voluntary. Farmers or growers will enroll in the program, and if a certain trigger level is met during a drought, which I think is the index well being below 635 feet on October 1st, then the next year they would give up the amount of agreed water in exchange for a payment. So, it's a win-win for the people who enroll in it, because they can get paid for the water that they're not using it, but then the aquifer also gets preserve those spring flows, because you can imagine how valuable Comal Springs is to those people who are in that community, not just to the endangered species, but there's a whole economy built around the springs, and the downstream users also rely on that. So
now, Jim, is it true that the model kind of helps dictate how much water is leased in order to protect that minimum spring flow? Like, how do they obtain that final number that they need?
So the agreed thing in the Habitat Conservation Program was based on some biological science and more or less expert judgment that 30 CFS, cubic feet per second, of water needs to be maintained at Comal Springs to keep that habitat from dying out. And at 45 cubic feet per second at San Marcos Springs, and that's where you got the Texas wild rice and a few other species that rely on that water. So in the model, what we'll do is rerun it. And so at the beginning of the HCP program, when we ran this scenario with all the pumping and the conservation measures, the model didn't quite say it would stay at 30 CFS during that minimum flow during the worst part of the drought. And it actually came down at like 29 cubic feet per second. But so one of the exercises we did is, well, how much extra voluntary irrigation suspension would we need to get it right at that 30 and, keep all the boxes checked on our permit? And so because of the modeling effort, we identified that we need to enroll an additional 1,795 acre feet into that program, which they have done. And so that's now the new VISPO standard, and that's based on the model.
That's incredibly precise. So if you were working with the model, could you look at the historical data and plug it in? If you were trying to get today's readings, how close would the model get to what the springs are flowing at today and what J17 is at today? If you plugged in data to look at today specifically, how accurate would it be?
Well, we did what we call a verification process. We calibrated the model up through 2012, and then we held back 5 years of data to run the model forward and see how well it matched. And it did a pretty good job, because it was the last part of the drought we went through between 2010 and 2015, or before it broke, and it matched that pretty good. And in any one month, it may be off by a few feet at the index well or 10 CFS at the spring flow, but on average, the errors are, there's equal errors above as there are below. So on average, you're getting it right.
So the model is always constantly evolving, like you were saying, that you're constantly plugging in numbers. So it's not like it's ever just going to be complete.
Well, we can say that we've demonstrated to satisfaction of all these expert review panels and the National Academy and Fish and Wildlife Service that our program is effective. So
yes,
unless something comes out to cast that into doubt, we don't really need to keep running that same simulation over and over. But we do continue to process the pumping data and the water level data, because eventually somebody's going to want to update and try to make another round of improvements. Get the model as best you can, and the model kind of where you have trouble predicting things, maybe tell you where you got to collect some more data. You collect the more data, you update your conceptual model, and so you make some tweaks, and you run it again. And that can be like a 5-year process to go through all that. So you kind of, when you update your model, you get all the answers that you can as best you can, then you kind of go back into the new phase where you're kind of keep collecting data, keep thinking about it until you learn something new that may be significantly different than your original model.
That brings me to my next question, Jim. So the model is based on historical data, and that kind of assumes that we're going to get the same types of weather and climate moving forward. But as we all know, that there's climate change ongoing in the future that causes a great amount of uncertainty, including the duration and length of and severity of droughts, potentially the severity and types of storms that we see. So what is the modeling group doing to incorporate climate science and future predictions?
Well, that's actually our next future-looking goal, and we've already started on it. Now that we've gotten through the phase 2 of the Habitat Conservation Program, we're looking toward 2028, when the current the incidental take permit expires. It has to be renewed. So we're hearing from Fish and Wildlife Service that they would want us to have thoroughly considered how future climate effects are before they may give us another 30-year permit, say, for example, to manage the aquifer. They want to know that these conservation measures are still going to be effective into the future, and that future, more than likely, is going to include some climate change. And there's a lot of uncertainty as exactly what that change is. It's more certain that it's going to be warmer, but we don't know what humans are going to do to curb their carbon emissions. So we have to look at different scenarios. One would be like the business as usual scenario. We keep using fossil fuels and don't change our habits, and so it'll warm a little faster. Another scenario would be it takes us a while, but we finally reduce carbon emissions to net zero around 2050 or something. So that's another scenario that they run through the global climate models. So we don't do the global climate modeling. What we do is we take the results, and there's, I think at last count, somewhere between 20 and 25 widely accepted modeling groups around the world that generate these scenarios. And you want to consider a lot of different scenarios, because no one is going to nail it just right. But the ensemble of all those models, if they're all consistent and showing warming and changing in rain patterns, then you can have some confidence that you at least consider the range of what might happen, right? So that's kind of where we're at now. We're taking those global climate model results, and these are big data sets. I mean, it's for the whole world, so we got to focus in on what did they say about our region. And like one cell in these global models would be almost the size of Oklahoma, or 2-3 model cells, or Texas. So they have to do this process called downscaling, where they take what the global model predicts and then they compare that to local observations. And then there's statistical methods that you can kind of correct any bias, because it's these global models aren't giving you for your precise location, they're giving you an average over a big area. So you can adjust it if you're in the east or west of that area, you can adjust it. So we're in that process now, and we got all these models, most of them run from, they'll go back 30 years, like maybe, yeah, since 2050, a lot of them go, and that's their calibration period. So because you want to demonstrate that your model matches the weather patterns that have been observed to date, and then you run it forward with higher carbon dioxide, forcing more heat to be retained in the atmosphere, and see what it says, how that affects all the other processes, including ocean circulation, atmospheric patterns, hurricane cyclone formation, and of course surface temperature is the one you hear a lot about. And people always say about global warming, but it's really changing climate.
Wow, that's so impressive, Jim. So can you explain to us a little bit like the brilliant minds that are on your team and kind of what each of them does? I know you said it's a smaller team, but can you kind of highlight the things that they do?
Yeah, we got a good team for a small agency. It's 4 of us, including me. So I'm sort of the director. I kind of have the big picture and try to make sure we have all the resources we need, and try to set up collaborations with outside agencies. And then we have an aquifer data analyst named Ned Troshinoff. He's kind of the guy that has his finger on the pulse of all the data that's being collected that could be of use to us. And he pulls it together into a geologic layer model of the aquifer that he's been working on. Really cool 3D expression of the aquifer that shows all the faults and where all the wells are drilled.
Wow.
And then he also keeps track of all the pumping data. There's all these meter records from the meters team that we have to review and try to convert that into a monthly pumping totals instead of just annual. And then there's the water level observations and the spring flow observation. It's a lot of data for one guy to pull all together. Well, there's a whole data collection team that he's getting it from, and he's got to QA it and put it in the model for me. Then we have 2 senior modelers that are kind of PhD level scientists that are really good at their jobs, is what I can say.
Yeah.
They have a lot of experience with advanced mathematics, programming for data processing, and then running not just groundwater models, but we also have a set of watershed models. And we're also looking into some new things. A lot of people hear nowadays about machine learning or artificial intelligence or deep learning. There's a lot of phrases for basically the same thing, is where there's these algorithms where if you have any kind of process that has inputs and outputs, you can use these algorithms to try to figure out how you can predict by just the computer just searches for statistical correlations between inputs and outputs. So you can feed it all your weather data and use it to estimate, based on how much it rained or what, number of sunny days or
Wow.
temperature, humidity, things like that. You feed it all in, and we're having some success. There's actually been one journal paper published by Khan earlier this year that it was a start in that direction. We're predicting evaporation rates, which is an important input to us when we're trying to see how recharge might change in the future. So we're looking at these machine learning methods to if we can get them to be able to predict spring flows or water levels, which, like I said, the results are encouraging so far, but we're just beginning. Then you can give it the input from the climate models, saying, well, here's how the temperature things change. How does that affect recharge? So that's one thing we're looking at. And we're also using physical watershed models that can be used to calculate recharge. So those are more like actually modeling the process using the equations for infiltration. If it rains harder, then the ground can infiltrate, then you get runoff. Then you get runoff becomes a stream flow. The stream flow goes into the aquifer. So we're actually physically modeling those processes in a computer, similar to how the groundwater model works, but it's all surface process based. So we also can calibrate those for the past and then run those into the future using climate inputs. And that we're still in the early stage of that, but we're making good progress. So we hope to say that how, as I was telling earlier, we're trying to protect the aquifer to repeat of these drought of record conditions. So probably more than likely the climate is going to affect the aquifer. It's going to be hotter, so you're going to have more evaporation. But will it be worse than that drought of record that we're already predicting? And then what we know through tree ring analysis and things like that is in fossil records and such, that that drought of record was a very severe drought, like the kind you might only see once every 500 or 1,000 years, where you got 10 consecutive very dry years. So that might become more likely. Maybe instead of a once every 500 year kind of event, it's a once every 200 year kind of event. So the question is, is that still protective? How could we expect conditions that are even worse than that?
So if we, I see. So if we kind of continue on like this trajectory of how we're kind of going about things and using resources, and essentially it does affect the aquifer that we rely on.
Yeah, it almost seems unfair some ways. Is that we have to show that we can protect against climate change, but the whole Earth has to cooperate to not impose that condition on us. But we'll do what we can do. I think we don't really know how it's going to affect it. We know it's going to get hotter. Not sure by how much, because a lot of that depends on what human choices are, fossil emission wise, and then but it's going to be warmer. And some of the models say that precipitation will become more variable, where you can get more intense rainfalls. That could actually be good for recharge, because more intense rain gives you more runoff onto your recharge.
Now, Jim, circling back to this concept of using artificial intelligence and machine learning to help plug in some of these variables, are we also working with academic institutions to help work on this issue together?
Oh yeah, we've partnered with there's a couple agencies. The University of Texas at San Antonio has got some good talent there, and partnering with us, we developed this collaboration where they, as a research institution, can apply for federal grants, but they need a problem to work on to show the grant givers that it's an important problem to society. Well, what's more important than water supply for a region as big as ours? So we've partnered with them, giving them our data, and our problem statement is that we need to know how climate's going to affect us. And so they actually have received a grant from another agency that we collaborate with. It's the South Central Climate Adaptation Science Center, which is run by the U.S. Geological Survey in cooperation with the University of Oklahoma and some Indian native tribes, and some other stakeholders are involved in it. But anyway, they have grant money to give away, and UTSA was just recently, last week, got notice that the proposal that they jointly developed with us is being funded for $298,000 over a 2-year period, which that'll fund a couple of PhD students. And
hey, congratulations!
Yeah.
And so yeah, that these. It's a way to get extra mileage. So none of that money comes to us, the Aquifer Authority, but it's going to a university supporting local students to get their education and work on a problem that is important to our local community. So that's exactly the kind of collaborations we want to support. And I feel good that we're kind of having some success in that. And I think there's we have other collaborations where we get free advice with with federal agencies and outside expert review panels.
So it's kind of like that ripple effect. It's like you're doing this work and you're collaborating with these universities or these agencies outside of the EAA to kind of do that ripple effect to get people all on the same page, all working towards like inspiring the next generation to maybe do something with this information, or continuing on kind of that legacy of what do we do next? How do we help the aquifer?
Yeah, it's really win-win. We're supporting the community by helping them to get these federal grants that support the students here in Texas that are going to UTSA. We have an internship program with not just UTSA, but any college who wants to apply for that. So we have a modeling intern pretty much every semester that we support. And right now that is with UTSA, but we've collaborated with Trinity University students, St. Mary's University students, and lots of others over the years. So I think it's important that these problems that we're trying to solve, have an opportunity for members of our community to participate and learn from it and benefit from it.
Yeah, Jim, that's a great point. And I've truly enjoyed our conversation so far, helping us and others understand what these models do and how they benefit the aquifer. As I understand it, Jim, that you're on the cusp of retirement here. And I'd like to give you a few minutes here if you want to talk about what that means to you and how this program has been part of your career and what it means to you.
Yeah, I've had a pretty interesting career, from everything from doing research up on the Greenland ice sheet to, going in underground tunnels beneath the Nevada test site. But I'd say the most rewarding has been here because I feel like I mentioned earlier, it's a local problem. It benefits the people in my community, our community, and you can see the results. So we came in, we kind of had a modeling program that relied on outside consultants to do a lot of the work, but now we got some really bright people who were collaborating with outside agencies, but we have the capability to do that work and have it be a source for other people to get grant funding so that they can help us support our work. So I feel like that's probably one of the most rewarding aspects of the career I've had. And so you'll still have me around at least to January, and I'll always be available for any sort of free advice you guys want.
So that's a beautiful thing, I would say. And thanks to all that you've done, because essentially what you're saying is we kind of started maybe in a semi-decent spot with modeling, but since you've been there in the inception of the modeling team and the growth of it, you've seen it evolve and grow to something bigger than what probably they thought it was going to start out to be, correct?
Well, I don't know about bigger, but better, I hope.
Yeah.
In terms of our in-house capability. Like our original groundwater model, we paid U.S. Geological Survey to build that for us, and we just sort of, fed them the data and gave them feedback where we could. And that gets to be a pretty expensive endeavor when you're paying outside consultants. But I feel like we've developed that capability and the confidence to do that ourselves, and to have people know that we're not just a small shop. We have experts that are being published in scientific journals and recognized around the academic community too.
Well, Jim, I want to congratulate you on a terrific career and having helped build this legacy with this model and other information that's going to help us not only right now, but in the future as we plan for this system. And thank you so much for joining us today on the Recharge Zone podcast. And we're so grateful that you were able to come today.
Thanks, Ann-Margaret. Thanks, Brent.
Thanks. All right, y'all. Well, we thank you for tuning in to this episode of the Recharge Zone podcast. And we appreciate all of our listeners that have tuned in to our first season of the official podcast for the Edwards Aquifer Authority. Happy holidays, y'all, and stay tuned for Season 2 of the Recharge Zone podcast, set to air in January 2021. Have questions? Ideas for topics? Or things you want to learn more about? Well, reach out to us by emailing us at rechargezone@edwardsaquifer.org.